circular, a helical moment. And this helical moment is very much dependent on how you orient themselves. And you can clearly look into that. This helix structure is already helical. That means it's already have a handedness. So it doesn't matter. Even if you create this alpha helix with all glycine, will it be optically active? If you create an alpha helix with only glycine, will it be optically active?
Okay.
Yes or no?
Yes.
Yes, it
Yes.
would be active because the structure itself has a handedness now. It doesn't matter which actually makes the molecule. It all depends whether the molecule has a inbuilt chirality or handedness or not. So when I'm creating the helix structure, as I showed you earlier, it has a handedness. It can be either this anti-clockwise motion or it can be a clockwise motion like that. Okay. So depending on that, it can actually have this particular kind of helicity already inbuilt, and depending on the helicity it will create the CD activity. Okay, it doesn't matter what is the constituents made out of that. The constituents are chiral, it will show some differences, that's all, but the chirality will be present. Okay, so the chirality has two phases. One is what it is made out of, and second is what is the overall structure. Now if you remember what Professor Chidambar Kulkarni was discussing at that time, that some of the system which are actually not even chiral, when it is forming the polymer, it is giving me chiral signals. Okay, why? Because when it is forming the supramolecular larger structure, it is creating some helicity or handedness somewhere, and that is actually the reason of the CD spectrum. Similarly over here, when you're forming an alpha helix, over there you can see this helical structure very closely, and you can see there's a handedness. There's a way it can rotate, and you can rotate in two different ways, either clockwise or anti-clockwise. And these clockwise and anti-clockwise are actually exactly mirror image of each other and don't superimpose or indistinguishable structure. Or in other way, you can say, actually, if you do it, you cannot find a improper axis of rotation. Or in the other way, you can say it belongs to either a CN or DN point group. So either way you want to describe that, if you create a helix, that means you created a handedness or a directionless direction over there in the system, which actually have a chirality, inbuilt chirality. So that's why this system becomes chiral. Okay. Now, why a beta sheet is chiral? Again, the same thing, whether it is parallel or anti-parallel, depending on that, it is creating a system. It is creating a directionality. It makes sure that this protein structure, the backbone, will be staying like in this particular direction. So over there, depending on this parallel and anti-parallel, you can say it is a parallel like that. So that means you can create an anti-parallel system like that. Or you are creating an anti-parallel system like that, you can create over there a structure which is actually parallel to this particular system. Okay, so these kind of systems are actually all possible, which are again following the same trend what we are actually discussing. And these two systems are not same. These two systems are not same. So that's why a beta sheet also a chiral system because of the overall secondary structure. And what about the random coil? Random coil is more or less mostly coming because it is having the chiral constituents, because overall it doesn't have or may not have the overall structure. It is much more flexible, it's much more fluxional, it is changing a lot. Whereas alpha helix and beta sheet are kind of robust. Once it forms an alpha helix, it stays alpha helix. When you form a beta sheet parallel or anti-parallel, it will stay as a beta sheet parallel or anti-parallel. Random coil is much more fluxional system. But over here, if I take a glycine, it possibly may not show a random coil CD signature. But whereas other than all the glycine which are actually forming this random coils, over there you might going to see a CD signature. Okay, so is it clear why alpha helix and beta sheet especially show CD spectra? It is not only because their constituents are chiral, because all of the overall structure of the backbone. Is it clear to everyone? If yes, then I'll go to the next one. So over here, I'm going to show you the alpha helix, beta sheet, and random coil structure, how the CD actually looks like. Okay. So this is the CD structure of alpha helix, beta sheet, and random coil. Okay, and I'm going to follow the same color what they are showing. So random coil, they have used this gray color. So I'm using it in gray. Alpha helix, they are using blue, a little bit darker blue. So it is the alpha helical system. Sorry. This is the alpha helical system. So this is the alpha helix. And in the beta sheet, they're using a saffron color. So in beta sheet, there I'm drawing an anti-parallel beta sheet. This is the structure. And now take a look, what is the overall signature of the system? Coming one by one. First, alpha helix. Now, alpha helix always have a positive band, a positive peak around 190 nanometer. Okay, so what is shown as over there at 190 nanometer. So you can write it a positive signal around 190 nanometer. And now if everybody is thinking about what is positive and negative, again, look into there, what it is given as molar ellipticity, which for now, believe it is the psi. Over here, it is the positive. Over here, it is the negative. And I have gone through that, why it is positive and negative, because psi is nothing but a difference between absorbance of the left-hand circularly polarized light and right-hand circularly polarized light. Remember, I guess? And that's why, depending on that, which one is absorbing more, you can have a positive or a negative. So alpha helix, any alpha helix you found in protein structure anywhere in the world or anywhere in the universe, what you're going to see if you do the CD spectroscopy, you're going to see this 190 nanometer band in the positive mode. Then you can see it is coming down, and then there is a band over here. Actually have like two different bands, two negative signals, one at 208 nanometer and one at 222 nanometer. Okay, and over there, see the difference between them. The 222 nanometer band is generally a little bit more, actually stronger compared to the 208. Okay, if you take 208 and 222, 222 will always be stronger than the previous one. So if you shrink that down, so probably it's better shown in the previous one. So over there, you can see that over here, this is the 208, this is the 222. You can clearly see that 222 can be seen very easily, a little bit on the lower side. Okay, so that is the reason. So that is what alpha helical bundle looks like in CD spectroscopy. So what are the important things? 190 nanometer positive band, 208 negative, 222 negative band, and 222 negative band is stronger compared to the 208. So you get twin bands or two different bands in the negative format. Now come to the beta one. In the beta sheet, look into that. Over there again, you have a positive band around 195, which is a little bit shifted. So it's around 195 nanometer. However, the main difference comes when it goes to the negative region. In the negative region, it has only one band. Okay, negative region, it has only one band, and that is around 280 nanometer. So how you are going to differentiate between alpha helix and beta sheet in CD spectroscopy? You look into how many bands you are actually seeing in the CD signal in the negative region. If it is two bands, 208, 222, it is alpha helix. You are seeing only one band at 280 nanometer, it is a beta sheet. Fine. Okay. And random coil is very easy to find because it actually starts with a negative signal around 195 nanometer. So previously, alpha helix and beta sheet, both of them has positive signal in this region. Whereas for beta sheet, it is 195, alpha helix is 193, but for random coil, it is actually starting from negative region. And then it start to move positive, but over here is a very weak signal, very hard to see. It is almost close to the zero line, but it goes a little bit on the positive, but there is no direct band. You can say it's like a broad band going from say like 210 to 230 nanometer or so. So it goes to positive region and a very broad system from 210 to 230 nanometer. So with these particular signatures, you can find out whether you have an alpha helix or beta sheet in the system. Okay. Anybody have any query up to here? How we can differentiate different protein structure with CT spectroscopy? Yes, please go
Sir,
Sir,
my question
first,
is,
ahead. Okay, one by one. Okay, Chandan, please ask first.
sir, here if for the alpha helix, we can the different three types of peak. Now, sir, if the amino, it depends on if I am asking that it does not depends upon the amino acid linkage or what type. It only depends upon the only for
Overall
depends upon
structure.
the special structure.
Yes. Yes. So if I understand your question, so if say I am making alpha helix out of all glycine versus all alanine or a mixture of different amino acids,
Yes, sir.
does all the alpha helix look similar CT spectra or different CT spectra, right?
Yeah. Yes, sir.
Yeah. So the answer is all of them will give same CT spectra because it only depends how the spatial orientation of the amino acid backbone. It doesn't matter whether you have glycine, alanine, or any other amino acid. The amino acid backbone is made out of amide bonds, right?
Okay.
And how the amino acid backbone, that means the amide bonds are spatially oriented. It is like this particular alpha helix bundle, whereas the first and fourth are on top of each other. Okay, and that is independent of what is the particular sequence is. And that's why what happens that your CD spectra will also be the same. Okay, it doesn't matter what is the sequence. It matters whether it forms the alpha helix or not, which actually shows that when it alpha helix is formed, doesn't matter on the sequence, the 3D orientation of this helical structure is pretty much same. Does it answer your question?
Yes, sir. Sir, another question. Sir,
Yes, so
when you
please
do...
hold your question for a minute. Let me answer Ghazal's one first.
Okay, sir.
Yes,
Thank you.
sir, my query was the same only. This
Okay,
only I
so
wanted
good.
to
So
know.
everyone's thinking the same. Okay, now shoot the second question, Chandan.
Okay, sir. Sir, for the when you do the CD spectra of the protein, just I take the alpha part of this and I do the CD spectra of the alpha, and we get the three peaks
Yes.
in three different wavelengths. But sir, how we can get why we can get the three peak at this point? What?
Yeah, that is a question which is probably going to give in the quiz or in the NCM exam. I'll give you some hints, but you have to answer this question on your own. Okay, that is how do you go through a PhD course? I'm not going to answer everything. You have to find something else. The question is very nice, and everybody, I think, probably having the same question in their mind if they're listening. It is that why this alpha helix is giving this particular band and especially this particular three peaks in this particular region. Okay, so I'll give the hint at the end of this particular portion. Okay, we'll come into that. So any more question, anyone?
So my
Sir,
question is like why we have taken this wavelength.
Yes, I'll come into that. I'll come into that. Why particular this wavelength and why we got this kind of signals. We'll come into that. Okay, anything else? Yes,
Sir, if left-handed alpha helix will show the positive peak in region 190, then right-handed will be the same.
Yes, the right-handed will be the exactly opposite. Okay, it depends on the orientation. So because we have L amino acid is formed in one particular direction. Okay, if you take the D amino acid, it will be the opposite. If that is what you're asking. Okay, because due to the presence of this L or D amino acid, its orientation changes. Right, we'll come into another interesting example of that when we discuss the DNA today and how that particular orientation actually changes. Okay, so that is because of the how the orientation of the amide bonds will be on the structure. That is what is going to decide that. And your answer, your thought is actually correct. If I take the opposite one, it will be exactly opposite. Okay. And as we discussed, because it is enantiomer, one enantiomer showing in this way, the other will be exactly the opposite. Okay.